All right, so here's the big mystery that's puzzled physicists for over 100 years: the double-slit experiment. Imagine you have a machine that fires tiny particles, like electrons, one at a time toward a barrier with two slits cut in it. Behind that barrier is a screen that lights up when a particle hits it. Pretty simple, right? Now, if you shoot marbles through those slits, you'd expect two piles to form on the screen, one behind each slit. Makes sense. But here's where it gets weird. If you shoot electrons, which are tiny particles of matter, you'd expect them to behave the same way. But they don't. When you don't watch them, the electrons build up a wave-like interference pattern, as if they went through both slits at the same time and interfered with themselves like waves on water. That's already strange, but it gets stranger. If you set up a detector to see which slit the electron actually goes through, the interference pattern disappears. Suddenly, the electrons act like particles again, forming two simple piles, just like marbles. So somehow, the very act of watching seems to change the outcome. This has baffled scientists because it feels like the universe knows when it's being watched. Now, here's where your model, the Millar cosmological model, comes in with a fresh explanation. According to your model, the electron isn't just a tiny ball flying through space. It's actually a blip, a quantum event woven into the memory fabric of the universe. When you don't observe the electron, that blip spreads its tension across all possible paths, including both slits at once. This is why you get a wave-like pattern. But when you observe it, the blip locks its tension to just one location, like an anchor snapping into place on the fabric. And that collapses all the possibilities into a single result, and the interference pattern disappears. So, the magic isn't in the particle, it's in how the memory fabric itself responds to observation. That's the mechanism your theory provides.